Good afternoon, everyone. I'm back. I'm going to be working through a few more convergence tests today. As the lesson's title at the top says, we're going to be looking at two tests. One of them is called the integral test. It uses, well, as you'd expect, integrals. The other one is called the p-Series test, and even though I do once again have my hydro flask, and I'm probably going to need to pee at some point, at the same time, it's a little bit different than that. I will say, as far as just kind of a general preview, the integral test tends to be pretty cumbersome. It's very nitty-gritty and involves a bunch of different concepts from Calculus BC's first chunk. The p-Series test is as simple as looking at something and going, how does it compare to a particular number? So I think you'll find the p-Series to be a nice thing at the end. If you're looking down, I guess I actually covered up so you can't see how many pages there are. There are a bunch of pages here. Some of them are proofs, in which case I'm just going to kind of talk through them very briefly. Some of them are examples that take a single line of work, particularly when we get to p-Series. And of course, then I've got multiple triads that are mixed in as well. As far as kind of a daily check-in, for me, it's I don't even keep track of days of the week anymore. What is it? It's Wednesday, the 18th of March. So for this moment, I don't know, at this point, Tom Brady is a Buccaneer, so there's that. Other than that, it's just kind of another day trying to get used to the new normal of all this. So I'm hoping to make a short trip into school tomorrow to pick up some stuff. Other than that, I've got a bunch of ideas in my head, some of which you'll hopefully hear from me about later on this year that we're looking at. And obviously I also have other things to say as we get further along, but for the sake of maintaining focus, I'm just going to not say any of those things. So instead, I'm just going to start talking about the calculus material and try to make sure I can at least shepherd you through the rest of this curriculum and feel like at least in that way I've given you what I had promised to give you and will give you. So having said that, we have the integral test and p-Series. So the next two topics in this unit of convergence tests. So to start things off, as I mentioned, we're going to talk about the integral test. The integral test is a way of using the value of a particular improper integral. In fact, I should probably just be making some notes over here. We're going to use a particular improper integral and determine whether that improper integral converges or diverges. And then it's going to sound weird when I say it, but then somehow, by looking at that improper integral, we're going to be able to tell if the series actually converges or diverges. That's kind of the lay of the land here. So things to note about this particular test is there's a set of 3 initial conditions that have to be met in order for a particular series to be eligible to use the integral test. And if memory serves, whatever the AP test potentially looks like this year, I believe those properties have come up multiple times on old exams. So the things that are required for the integral test is that your function that you're analyzing, which if you're looking ahead and just kind of ignoring me but looking at the stuff here, it's talking about a function f, but also talking about a sequence a sub n, which is equal to f of n. However you want to think about it, either the sequence or series terms or the function f. If that function is positive, continuous, and decreasing for all values of x greater than or equal to 1, also, by the way, then n greater than or equal to 1, then we can use the integral itself, the improper one, to determine whether or not the series will converge or diverge. It seems a little strange, but it's basically like there's some sort of pairing that's going to happen here. If the improper integral diverges, then the series diverges. If the integral or the improper integral converges, then so will the series. So basically we can use the integral in place of the excuse me. We can use the series or the integral in place of the series and come to the same conclusion we were looking for anyway. So again, this is probably the most important thing. If you're writing notes down, I'm not actually sure if people are doing that, but if you're writing things down, that is the most important piece to record down. But of course, I'm realizing that you have the ability to pause. So I guess I can move on from there and start to show you what this works like. Now, before we get in, I mentioned that some of the pages are just proofs. Here's the proof of the integral test. And truthfully, I'm sure this isn't your favorite thing to look at, no matter what the circumstances are. But at the same time, I think this is pretty clever. And I've written it out myself. You can tell I've written it out myself very carefully because it's actually super neat and nothing slanting or weird or anything. But basically, it turns out that the way you can prove the integral test is simply by using LRAM or RRAM and just arranging things in just the perfect way. So just to kind of give you a quick rundown, I'm not going to go into this in depth, and obviously you won't be assessed on the proof of the integral test. Maybe if you take real analysis someday in the future, but definitely not here. But basically what we do in this case is we take our interval with a V, from 1 to n, and we divide it up into n minus 1 rectangles. And there's a very particular reason why we do n minus 1, and that's because we pick a number of rectangles that matches the width of the interval. Because that way, each of those subintervals, has a width of 1. And the reason we want them to have a width of 1 comes from the fact that when we go to do RRAM or LRAM, since the area of each rectangle is equal to width times height, oops, that's an M, width times height, what that means is the areas in our case are going to be 1 times a particular function value each time. So in other words, the areas for each of those rectangles will just be equal to f of n. So specifically, we're choosing it this way very particularly and purposefully so that way we can, in a sense, make everything look cleaner in our computation. So having done that, because we've guaranteed that our function is positive and decreasing, so remember those are two of our necessary conditions for this particular theorem to hold, or this particular test to work. Because of that, we have a decreasing, continuous, and positive function. And that means if we use RRAM, we're going to have an underestimate, and if we use LRAM, we're going to have an overestimate. And what that does is it allows us to bound our value of the integral between two values that we can calculate. So in this line, and once again, you don't have to know this, I'm just kind of talking it through as I would in class, really briefly. If you do the RRAM or the LRAM, if you do the estimates using those values, you get a sum of f values, one of which is bigger than the integral's value and one of which is below the integral's value. Because keep in mind, the integral's value would be the actual area underneath here, not the estimated version, but the actual area if we went all the way to infinity and calculated that out. So having done that, what we find out is that the integral has to be greater than or equal to one value and less than or equal to another value. And then we find very quickly that the sum of those things is bounded, and because that sum is monotonic, because it's decreasing, we have proven that the sequence of partial sums, I guess is the best way to put it, that sequence of partial sums is actually a bounded monotonic sequence. And since we talked about that a couple days before, it's true that the series must converge. So, and from there, we did it with the converging version. There's another version that does things for the divergent one. I just think this is the more clever of the two. Now, having said that, I imagine most of you will probably skip paying too close attention here, and that's totally fine. But at the very least, you have a resource that has a really neatly and I would say beautifully written out version of this proof in case you're curious why the integral test works. And again, weirdly enough, it's all RRAM and LRAM. Not your RAM nor my RAM, but our RAM. Let's go just a little longer than I expect. Okay, so now, having said that, let us dig in and start to look at some problems here. And first of all, I noticed that my purple has disappeared, and that bugs me. So I'm going to go grab it. That looks, I bet people are going to say, it's not purple, that's the wrong color. There we go. That's what I want. Okay, there we go. It's almost the same color as my stuff. By the way, no one's asked about my attire, but today I'm sporting a Franklin baseball cap, and as I have for all of these videos, I'm sporting a Franklin softball warm-up jacket. If I can get my hands on a Franklin volleyball, tennis, or track gear, I will absolutely wear those as well. So having said that, we just looked at the integral test, and in fact, I should probably go steal the integral test. That's it's my name. Might as well make it true, even if it's spelled a little bit differently. So I'll just kind of throw this up in the corner here for us. So there's the integral test in case we need to reference it. And what we're told is we want to determine the convergence of this particular series. Now, before we go in, there's going to be a clever person out there who's going to go, we don't need the integral test. And they're absolutely right, because truthfully, if we look at 42 over e to the n, I'm going to erase this in a second just so you know, that's the same thing as 42 times 1 over e to the n, which is the same thing as 42 times 1 over e to the n. And at that point, we can see that this is a geometric series, and we can see it that its ratio, its ratio is less than 1, because the ratio is 1 over 2.71, 828, 5, 3, 4, 5. I'm off a little bit. I'm rusty. But anyway, it's there. So that means that this series actually converges. So in other words, if you didn't want to use the integral test, you technically wouldn't have to in this case because this is a convergent geometric series. Having said that, nice try, buckaroo. I know how to beat you in this system. Watch this. Not the erasing part. That's not actually that remarkable. Use the integral test. So what I have determined, other than the convergence of this series, what I have determined over the integral, here's a second. What I've figured out over the last few years is that since the integral test isn't exactly the most practical tool of determining a series convergence or divergence, I've decided that this is the one series that I'm going to tell you when to use. I will tell you if I want you to use the integral test, to use the integral test to determine a particular series convergence or divergence. So in this case, as soon as I write this, as a terrible circle, but as soon as I write that, you can't get out of it. We now have to use the integral test. So having said that, and again, I want to make sure I include all the stuff here because it's easy to miss some of these pieces, especially when I'm not really focusing. The first thing we have to do before we can dig into anything with integrals is we have to answer the question, can we use it? Like, are we even eligible with this particular series to use the integral test? Because it's possible that maybe we can. Maybe it doesn't fit those three necessary conditions, positive, continuous, and decreasing. So in looking up here, we have to check each of those necessary conditions. So first, we're going to look and see, is this series positive? Or are its terms positive? And from here, what we can tell, or things that sometimes help, e to the n, that's 2.71828 something. So that's always going to be greater than or equal to 0. Excuse me, it's not even greater than or equal to 0. It's literally greater than 0. And that means that 42 over e to the n is greater than 0 also. And in fact, I think I technically should be saying x instead of n. Let me just make sure that's right. Yeah, I technically am. I'm supposed to talk about the eligibility of the function. So e to the x is greater than 0. 42 over e to the x equals 0. So the first property holds. This series has terms that are positive. Second, for continuous, the only place we could possibly have a continuity issue is with e to the x. But e to the x is greater than 0, which means 42 over e to the x is continuous, because that's the only potential place where the ratio of two things would possibly create an issue. So we also have a continuous function. And then finally, for decreasing, there are a bunch of different ways for you to check if a series is decreasing. Like, let's see, how did I do it last year? Oh, yeah. Okay, so what I did was I used it kind of analytically. I said e to the x is increasing, and that means that if we reverse that relationship, 42 divided by e to the x has to naturally be decreasing. So that is one way you could do that. Another way you could go through, by the way, if you wanted to, is you could rewrite this as 42 e to the negative x. This is kind of an alternate. Go 42 e to the negative x. You could take its derivative. So if you take the derivative of this guy, you get negative 42 e to the negative x. That's the same thing as negative 42 over e to the x, and that is always negative. So since the derivative is negative, that means that this entire thing is decreasing. The important thing for our purpose, though, is whether or not we did that. What we've just shown is that the integral test applies. So we are allowed to use the integral test to check whether or not this particular series converges or diverges. And again, at this moment, we're not sure if it does or doesn't, so we're going to play along. Well, I am, because the answer's right over there. But still. Okay, so having said that, where are we going to begin? Well, if you look at the integral test, it talks about this integral from 1 to infinity of f of x dx. So to start with, I want to analyze the integral from 1 to infinity of the corresponding improper integral. So 42 over e to the x dx. Now, before we do anything else, there are a couple things I need to take care of. This is something you maybe haven't thought about for a while, but because of that infinity, we unfortunately don't have it. We have what's called an improper integral. We don't have a definite integral that's between two finite values. So if you'll recall from a ways back, our solution to that problem is to rewrite this as the limit as b goes to infinity of the same integral, but instead of going from 1 to infinity, we're going to make it go from 1 to b. That way we have a finite interval that the definite integral is being evaluated on, and we just allow the limit to take care of the infinity part. As far as the inside, I'm going to make one more move too. I'm going to rewrite this as 42e to the negative x dx, and that way I've got an integrand that I can work with. Now at this point, because I got all the time in the world because I'm sitting here, I'm going to use substitution. Like again, you could probably think your way through this. This is kind of a calc sense level integral, at least anti-differentiation wise, excuse me. I'll let u equal negative x. That means du is going to be negative 1 du, or dx, excuse me. And that means that dx is going to be negative du. So having made that adjustment, what that allows us to do is to look at and analyze our limit as the limit as b goes to infinity of the integral from 1 to b of what will be rewritten here as 42e to the u. Oops, I missed a number in the 42, that's not like me. 42e to the u times negative du. And then cleaning this up a little bit, we can just rewrite this a little bit simpler, or a little bit easier to play with and look at. Write it as negative the integral from 1 to b. And technically the limits of integration are messed up. Forgive me. Don't want to do anything. No, I don't. Here. Let's do this. I'm going to ignore the improper integral for a second. I'm trying to be as formal as possible, but I just don't like it. So we'll go from there. So what does that mean? We need to anti-differentiate 42e to the u times negative du. That's the same thing as negative 42 integral of e to the u du. Do you see what that integral is equal to? There it is. Hopefully you du. I won't press it again. That becomes negative 42e to the u plus c, but we won't need that because this is a definite integral. And then I'll just make my back substitution and point out this is negative 42e to the negative x. So what you just saw was that I avoided dealing with the limit of integration for a little bit, avoided dealing with the limits for a little bit by just going through and handling the anti-differentiation, the indefinite integral part. Now I'll bring it all back. So at this point we're back to where we were. We now are going to be evaluating the limit as b goes to infinity of our antiderivative, which is negative 42e to the negative x, and we're going to evaluate that from 1 to b. Having done so, or being ready to do so, we then will still need the limit. I'll keep the limit in purple for a second. Do the limit as b goes to infinity. I'm going to rewrite this as negative 42 over e to the x. And then because we're evaluating it from 1 to b, I'm going to go ahead and just start plugging things in. So we'll have the antiderivative evaluated at b minus the antiderivative evaluated at 1. So having done that, we now get to actually see what happens here. So cleaning this up and also substituting for b. So b is going to infinity, so I'll just plug it in so we can look at it. This will be negative 42 over e to the infinity plus 42 over e. But remember, e to the infinity is so big, we might as well just call it infinity. And negative 42 over infinity is just equal to 0. So that means the value of this thing, this improper integral, is 42 over e, which is indeed a real number. So what does that tell us? Well, at this point, what we've just done is we've been able to draw a conclusion. This tells us that the integral from 1 to infinity of 42 over e to the x dx converges. Now I know it says it converges to 42 over e, but don't get too excited by the presence of that. That's not necessarily what the series will converge to. In fact, it's probably not. But at the very least for the moment, we've got that. We found that the improper integral converges. Why is that important? Well, it's because the integral test says that either both of these things, the integral and the series, either both converge or both diverge, which means that we can wrap this up because that implies that therefore our series from 1 to infinity of 42 over e to the n, it must also converge because it's got to do the same thing according to the integral test, and it converges by the integral test. We don't know what it converges to, or at least the integral test doesn't tell us. Of course, since this one's geometric, we could figure that out if we desired. But for the moment, all that really matters is that we've shown that it converges while using the integral test. So, voila. So obviously you can see this is not, like I said, this is not a practical thing. This is not a geometric series where you go, what's it say for the radius? Oh look, it's done. This is one where there's some nitty-gritty stuff. So this is like, from my end, if there were an exam, if there will be exams for this course, I would just literally ask you a single question and say, use the integral test to determine the convergence of this series. But you can see why. It's not the most practical one out there. So there it is, though. That is the integral test in action. So one good example. Having said that, seeing one good example doesn't replace seeing a couple good examples and kind of getting a feel for what's there. And of course, you have the ability to actually speed me up if you so desire and kind of move through some of this stuff while I'm working in real time. So if you want to, you can move forward if you want, but I think it's good to see a couple examples here and just kind of get used to the sort of work that's going to be done as you dig through these guys. So on the second example, we're asked to determine the convergence of this particular series. And notice that we're given the series in terms, so it's a little bit different than normal. In fact, I would say before we do anything else, it would be really important for us just to figure out what the heck does this series look like? So before we dig in, let's figure out an expression for the series, since we're going to need that for the integral test anyway. And in fact, I should point out as well, for the person that's like, oh, I don't want to, I'm going to do something else. I'm going to go teach myself the limit comparison test before, nope, you lost. And it's gone, because now I've put this in. So it says use the integral test to determine the convergence of this series. So, got you. Okay, so now as far as determining this series, it's important to start by figuring out what is the expression for this series, or what's the general term. Well, I see a 1 on top of all the fractions, so I'm just going to go with that. Then down below, I notice that we're adding 5 every time. So notice it's plus 5, plus 5. So that tells me that this is arithmetic. It's going to have rule 5n plus something. And we need it to be 47 when n equals 1. So if we want to get from 5 times 1 to 47, we need a 42. Oh yeah, that's right. I wrote these questions. I wrote these notes. Yes, exactly. That's there. Okay, so now having said that, we now have our expression. So that means that we're going to be thinking about this function, f of x equals 1 over 5x plus 42. So having said that, we need to start to analyze it. So the 3 properties that we need. First of all, do we have positive terms? And again, this isn't like the most formal thing in the world, but basically, since we're talking about x or n values greater than or equal to 1, that means that 5x plus 42 is greater than or equal to 0, and that means that 1 over 5x plus 42 is greater than or equal to 0 as well. So yes, we are positive. Am I sure? Yes, I'm positive. Second, for continuity, like do we have a continuous function for the parts that we need? Basically, the only time we wouldn't be continuous would be if 5x plus 42 equals 0, and that's going to happen only at x equals negative 42 over 5. But we've already established here that x is greater than or equal to 1, so we are indeed continuous. We don't have to worry about that other piece. Last but not least, we want to talk about decreasing. I'm just going to squeeze it in over here just to make sure that it's all in there. I want to see if this thing's decreasing. In this case, I'm going to use the derivative version. I'm just going to take the derivative and see what happens. So in this case, if I take the derivative of this thing, I'm going to think of this as the expression 5x plus 42 to the negative 1 power. That derivative is going to be negative this thing. Well, actually, I'll just go ahead and skip a couple steps. I think you're probably okay with this. 5x plus 42 squared. So in looking at this expression, the denominator is always greater than or equal to 0. The numerator is always less than 0. What that means is that this entire thing is negative, which means, of course, that we're decreasing. So that's what we wanted to see, was that we had a decreasing function, and this one is indeed strictly decreasing. So we're in good shape so far. We've got all the necessary conditions. What this means is that we can use, we can use the integral test. And this line, when I write we can use the integral test, you don't actually have to write. Although I guess if you have all the time in the world, which it kind of feels like we all do right now, if that happens, feel free to write this in. So we can use the integral test. So now, having said that, let's actually start to dig in. So we want to look at the integral from 1 to infinity of 1 over 5x plus 42 dx. So of course this is an improper integral. So just like I did on the previous page, I'm going to rewrite it as the limit as b goes to infinity of the integral from 1 to that value b. Hopefully that's not going to be a problem. And that's going to then be on the inside, 1 over 5x plus 42. Now before we go forward, I'm going to do this little trick. Oops, I forgot the dx. There, fix that problem. What I want to do here for a second is I just want to go do a little bit of a calculation off on the side. I want to figure out what's the integral of 1 over 5x plus 42 dx. Basically, I don't want to think about the limits of integration, just want to do the substitution work. Now I'm guessing many of you could do this in your head and get the 1/5 ln structure that's there, but just in case, because again, I have all the time in the world, we'll let u equal the denominator. Du will be 5 dx. That means dx will be 1/5 du. And that will give us the integral 1/5 1 over u du, which is going to lead us to 1/5 natural log of the absolute value of 5x plus 42. And of course there'd be a plus c, but since we're going to be doing this separately, we don't need to look at that. Having done that work, what we can now say is that this then leads us to the particular integral. Now that we have the antiderivative, we can now write this as the limit as b goes to infinity of our antiderivative, 1/5 the natural log of the absolute value of 5x plus 42, and we're going to evaluate it from 1 to b. Having done so, we can clean this up. We've got 1/5. It'll be the natural log of infinity. Well, I guess we should play this. I'll play it clearly. 5 times infinity plus 42 minus 1/5 the natural log of 5 times 1 plus 42. And then simplifying this expression out, we're going to get 1/5 of ln of infinity, oh boy, minus 1/5 the natural log of 47, which to be fair I'm kind of disappointed in. I'd prefer there be a 42, but yeah, whatever. Having said that though, the natural log of infinity is just infinity. So this is really infinity minus some number, which is just infinity. So having made that conclusion, by finishing there, what we've just shown, just like we did before but with converges, in this case we've just shown that this improper integral is divergent because its value is infinity. It's growing without bound. What that means is that our integral in question here, that one we were just looking at, that integral diverges. Simply because we just saw that it diverges because it goes towards infinity. It tends to infinity. Having said that, then we can finally make our conclusion at the very end. So let's see, what color do I want? What color do I want? Okay, right here. And since that integral diverges, the integral test says the integral and the series behave the same way. So we can therefore say that our sum from 1 to infinity of 1 over 5n plus 42, which of course is equivalent to this series we saw up above, we can say that that series behaves the same way, which means it diverges by the integral test. And as I write this down, I almost think that it should be called like the integral comparison test or something, but I guess that would be more words, and you probably don't want me giving anybody at College Board or in the math world more ideas. So instead I'll just stop and say what a great name integral test is. Test, more like fun walk in the park, with everyone 6 feet away from one another. Having said that though, there's the integral test. We've seen an example where everything converges. We've seen an example where everything diverges. And this one was good. This was a good example because we absolutely could not have used any other test that we've seen so far. Nth term test would have been inconclusive. It's not geometric. And oh wait, that's all we knew so far. So there it is. There's a good integral test one for you. Having said that, I want to give you the opportunity to work with the integral test a little bit. Truthfully, this may look like it's going to be tough because I've given you 2 questions on the integral test, but there's really not 2 questions. The first one asks you if you can use the integral test to show a particular series diverges, which the answer is yes or no in a short little explanation. And the second one asks you to actually use the integral test. And yes, that one will take a little bit of time and space, but that's why there's only really 2 questions here for you to work through. So as with before, the links to these try-its, the Google form-based try-its, are in the video description down below this video, or you can use the QR code and use a QR reader on your phone if you're doing this on a computer to access the try-it there as well. As with everything else here, it's completely optional, but obviously I encourage you to practice it a little bit. And in particular with this one, as you look at these 2, I would really recommend you look at the written solutions to the try-its that I'm posting in the drive, just because I have a feeling these are ones where just writing yes or no or converge diverge just doesn't necessarily get you the powerful like conclusion or satisfying. It's hard to know if you did it right just by writing converge, diverge, yes or no. So I highly recommend you look at those written solutions. Having said that, I'm going to take a short little break, and then I'll be right back to finish the rest of this too. So hopefully you use that to your advantage. Maybe you pause it with me in a sign of solidarity in these trying times. But hey, be you. Alrighty, as has been the absolute norm this week, whenever I take a break after finishing a section of one of these lessons, there's always 50 million emails to look at. I think in this case, the group chat fractured, and then there was a huge second group chat with tons of stuff talking about grading for term 3. Oh my gosh, there's a lot of other stuff. I also sang some songs, but those things are helpful when you're not feeling so good, as is pretending to talk to people that you like. So, having said that, let's kick back in with the second part. We've looked at the integral test. The integral test was really just a palate cleanser for this next test that's going to pop up. But the cool thing about this next test is it's far easier to use than the previous one. So here we go. So first thing we want to talk about, I know I mentioned that the title of the lesson you can already see because it's up there on the top, it's on the video, all that stuff, involves p-series. But before we want to get there, I want to talk about something called the harmonic series, because it turns out the harmonic series is probably one of the single most important series that's out there. This is one you definitely want to get series-is. So let's make sure that we have some understanding of the harmonic series. So first of all, the harmonic series is just the sum of all the reciprocals of the positive integers. So it's 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5. All of those things are sitting there. So basically, like the question, so right off the bat, it's a very simple thing. Keep in mind that although it might look to you like it's geometric, it's really not. Notice the differences just in these guys are not right there. Difference here is 1/2. The difference here is 1/6. The difference here is, I should be able to do this. This is 3/12, 4/12, 3/12. It's like 1/12. So obviously there's not a common ratio, and clearly we're not adding the same thing every single time. It's an easy to generate series, but it's not one that's easy to understand. Now, having said that, the question that comes up with the harmonic series, in addition to the fact that I have to tell you that you literally have to know the name harmonic series, it's kind of its own thing. The question, though, that's natural to follow is, does this harmonic series converge? And with terms that small, I mean, the terms are getting tiny. It definitely passes the, are the terms going to zero test. The terms are getting smaller and smaller. The question is, though, does it converge? And the answer to the question of does it converge comes from the integral test. In fact, the whole reason that we do the integral test first is it allows you to prove all these other properties of p-series. So the first thing to ask yourself is to look at the properties that are required to apply the integral test. Are the terms positive? 1 over something positive is clearly positive, so I'm good there. Second, is it decreasing? This is one of my favorite ways to go through. As n increases, as say it this way, as n increases, 1 over n decreases. It's that reciprocal relationship, so that's definitely true. And then continuous, it definitely is, as long as n does not equal 0. And of course here, we're talking about n greater than 1, greater than or equal to 1. So that means we're good. So the integral test can absolutely apply here. Now again, you're probably not thrilled about using the integral test, but I will say this is probably the easiest integral test application that I could probably give you. So having said that, let's set up the integral test and investigate. Because again, I bet your instinct is that this series converges. But you might be a little surprised. The answer to this question might diverge from your expectations. It was like 3 seconds too long. Okay, so in any event, let's do it this way. We want to investigate the behavior of the integral from 1 to infinity of 1 over x dx. Well, of course, it's an improper integral owing to the fact that it has that infinity, so we'll rewrite it as the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Now, unlike those previous problems that required some substitution to anti-differentiate through, this is easy. What function has derivative 1 over x? That's right, natural log. So really, we can actually jump right into the next step without much extra thinking here, and just point out that this is going to be the ln of x, and we're going to evaluate it from 1 to b. Now, prolonging the inevitable, while I think through my next move, that transforms this into the ln of b, and since b is going to infinity, I'm going to go ahead and drop the absolute values, and then we're going to subtract the ln of 1, which we know is 0, which means this integral is equal to the natural log of infinity. But wait, we already saw the natural log of infinity. I mean, infinity is going that way. ln of infinity is indeed infinity. So what that tells us is that our improper integral from 1 to infinity of 1 over x dx diverges. And according to the integral test, that means that we can therefore state that our sum, in other words, the sum or the harmonic series, is going to diverge as well. In fact, we'd say it diverges by the integral test. So in other words, even though these terms are getting smaller and smaller, it turns out that their sum is actually getting bigger and bigger over time. The more terms we add, the bigger it gets. Now, of course, we've just proven this, but sometimes proof doesn't necessarily convince you the same way it does me, who's gone through 3 years of upper division math and proofs and all sorts of stuff. So let's go to Desmos and see if Desmos actually confirms what we're thinking. Let's just see once. So I'm going to type in sum from 1, and I'm going to put in k here. I'll do 1 over n. Aha, it added the slider. I'm going to go from 1 to 100 first. So again, what we're looking at here is we want to see if it looks like this sum is getting bigger or not. Like, does it look like it's approaching something? So let's see. So at this point, like, the numbers are fairly small. Notice it's not really getting that big. I mean, they're 5 after 5.18 after all those terms. Let's go to 1,000. Let's see what happens here. Oh, shit, I forgot I can't do that. After 1,000 terms, we're only at 7. Like, gosh darn it, this ain't growing that fast. Let's try 100,000. I don't know if it'll like me, but look at that. After 100,000 terms, we're only at 12. But here's the thing. Have you seen any evidence that this is actually starting to flatten out? I'm guessing the answer is no. And in fact, the answer is no. I'll even put a few more in there. The answer is no. We're going up to the millions, and we're still growing. Not fast at all. It's very steady, flat growth. But it's definitely not flattening. It just keeps getting bigger and bigger. And in fact, let's see once. I put this in there. Look at that. It almost looks like it's going to be begging something, but then something funny happens. It just kind of keeps growing. It's not growing fast, but it's just growing. In fact, let me try something. I don't know if this is going to work, but again, I haven't tested all of these things out. Ha! Look at that. Notice. Okay, so let me zoom back a little bit here. I don't know if you can tell what I was doing. I was basically just adding numbers so that the basis was... Okay, well, it's not working anymore. What I was trying to do is I was trying to show you that it just kept going up in the same way. But basically what we're seeing here is that this sum just doesn't approach anything. It just kind of hangs around. And it keeps getting bigger and bigger, which unfortunately is not what we're looking for in a convergent series. So that's just another way to kind of confirm the idea that the harmonic series actually diverges. And in fact, it is a divergent series, and in fact, we'll see in just a little bit that it's what I'd call the boundary between all the divergent p-series and all the convergent ones. Now, having said that, if you didn't like any of the explanations I've seen so far, either the proof or going to Desmos and seeing it grow very steadily, but grow nonetheless, I have this thing that I came up with last year that I think it was someone that guided me through, maybe even a couple years ago. It might have even been Devon Herr. But basically, what I did here was I took a different approach to this, trying to show you that the harmonic series is in fact turning into a series that has an infinite sum. So what I did, and again, I'm not going to spend a lot of time on this. If you want to, pause it and kind of read through and look at it more in depth. But the idea is this. You can see it happening right over here. And again, we'll get to the application and the doing stuff in just a second. The idea is right here in this line. So the thing that you have to buy in order to make this work is the idea that if you take the series 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 forever onward, that's going to be equal to infinity and therefore diverge. I think it's a pretty safe thing to assume, but just to be safe, it's good to make note of it. Having said that then, what this convince me kind of leads you towards is the idea that you can write a series that's smaller than the harmonic series, but that ends up being equivalent to this thing that's equal to infinity. So right here what happens is I take those fractions that are not 1 over a power of 2, and I rewrite them as 1 over the next power of 2. The thought process being, with those two circled red things right there, that 1/4 is less than 1/3. So B is automatically going to be less than A. So that's our idea here, is that we're going to create a series where b is less than a. Like, and that seems fair. Like the sum is less than a. And then we do the same thing with 1/5, 1/6, 1/7. We replace them with 1/8. Then for the 9th, 10th, 11th, 12th, 13th, 14th, and 15th, we replace them with 1/16. What that does is it creates a bunch of things that always simplify to 1/2. And of course, we could keep doing the same thing. It'd just be with smaller and smaller fractions. But eventually, it turns out that b is just equal to 1 plus a bunch of halves. And since that's in a sum to infinity, like 1 plus an infinite number of 50-cent pieces is going to be an infinite number of money. Okay, that makes me want money. But beside the point, what that shows us is that b is actually infinity. So that means that the sum of a, the harmonic series, has to be larger than infinity. And guess what? The joke's on you. There is nothing bigger than infinity. Infinity is our conception. It's our numeric representation, or it's our symbolic representation of the biggest thing we can possibly conceive. At least, I guess it's countable infinity. Yeah, we don't want to talk about Aleph Null right now. But the idea is the harmonic series is bigger than something that's clearly divergent, and so that kind of gives us a little extra confirmation that, yeah, the harmonic series might not do it very fast, but it looks like the harmonic series does indeed diverge. So, having said all that, we're next going to talk about something called p-series. So, and again, like I've done with pretty much everything in this lesson, I've really broken up stuff into pages, not necessarily using space well, but it is what it is. So here is what a p-series is, and you'll notice that it looks very similar to a harmonic series, save one thing. It's basically, I was trying to think if there was a joke about the word urine in p, but I don't know, you're in luck that I haven't found it yet.
I didn't pee my pants. That was so funny.
I couldn't have scripted that. It literally did the pee my pants laugh on that one. So sometimes things line up. The rest of the world sucks right now, but that worked. So anyway, so this is a p-series. What I want to point out, in addition to pointing out the structure of the p-series, which is basically just 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p. Basically, this is what's called a p-series. Notice the structure here. We have 1 over every single time, and then we take all those positive integers and raise it to the p power. So notice that specific structure. And again, we'll talk about it a little more formally in just a second. Something that you'll probably want to note is that the harmonic series is the exact same thing as a p-series. Here, let me write this in there. The harmonic series is just p-series with p equaling 1. In fact, if you think about it, that should make perfect sense. Since the harmonic series was 1 over 1, 1 plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, plus dot, 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 you can just imagine that if we just added the little power in there, we'd have that clear structure. Same thing with the first one, you could write it like that. So we just have a p-series from before. So giving you an idea of some other p-series, just because we've only seen the one, we could talk about a great p-series like this one. Here, give me your favorite number, 42! Sorry, if that yelled in there. Yeah, we'll go 1 over n to the 42. So in this case, if we wanted to write out what that series looked like, it would be 1 over 1 to the 42, which is just 1, but 1 over 2 to the 42, plus 1 over 3 to the 42, plus 1 over 4 to the 42. So notice the p part is just really the power. And then, of course, I could write 1 over n to the 42 plus dot, dot, dot. So it's an infinite series. It's got, well, I guess I can't talk about countable infinity, but its denominators are powers of the positive integers. So there's where we are so far. Those are p-series. Having said that then, the test that will determine whether or not a particular p-series converges or diverges is all based on the value of p. Before we get there, what I want to point out is there are a few things here specifically to talk about with a p-series. Basically, first, the numerator must be 1. So otherwise it's not a p-series. So again, there are ways that we could use properties of series to then quickly conclude whether or not it converges or diverges. But for a p-series, it has to have a 1 up there. And that's a mistake I made my first couple of years. Shay, don't tell your older brothers. So don't tell Sean at least. I didn't teach AJBC, so I'm okay there. So having said that, that's the first thing. The second thing, and let me make sure I say this in there, the second thing is it's not a p-series until the p power is in the denominator. So theoretically, I could totally mess with people by putting in negative powers in there and leaving them in the numerator. Just make sure that it fits this exact structure. This is one of those structure matters situations where it's 1 over something to the p, 1 over n to the p specifically. So having said that, our conclusion, how we can tell if something converges? Well, the p-series will converge if the power p, again, fitting this structure, if the power p is greater than 1. On the other hand, the series will diverge, I should say diverges. It diverges if p is less than or equal to 1. And notice that we include the or equal to here, and the reason is the or equal to represents the harmonic series. The harmonic series is when p equals 1, and we already saw that that diverges by the integral test. So this is the p-series test. It's very easy to use and apply, and in fact I'll show you a couple examples here, and even a tougher one. I'll give you kind of the higher level example in just a little bit. But for the moment, just excuse me, just note how nice that series or how nice that test looks. Okay, so having said that, before we go forward, I know you're dying to see another proof. So here's another proof. Now again, this one I'm not going to dwell on very long. Let me just kind of talk you through the gist of what's here. This is another one where if you want to pause it and take a look, please do. But there's nothing really that interesting about this proof. It's just using the integral test 3 times. In fact, I should probably even write that up here. What did I do? Integral test 3 times. And the reason I did it 3 times was because there were 3 separate cases that were possible. We could have p equals 1. So if you had a p-series with p equals 1, that's literally the situation of the harmonic series. We saw that that diverged, so naturally it diverged here. Second, if p doesn't equal 1, p could be less than 1. Or it could be greater than 1. So in each case, I simplified and cleaned things up. You'll notice that work down here. And what I saw was if p was less than 1, it diverged, joining what we saw with the harmonic series. And if p was greater than 1, it converged. So therefore, we could use the integral test to prove it. So if you're ever curious how to prove p-series, and again, any individual one isn't difficult. It's only difficult here because we wanted to check for every possible p-value. We wanted to deal with all the p at once. Just funny to say. Sorry, I can't get past that joke. But in any event, we're just using the integral test to prove it. And again, if you don't like p-series and you want to use the integral test every time, be my guest. But if you use the integral test, you got to state those necessary conditions and do all that good stuff. So just buyer beware. As promised, though, let's look at a couple examples here. And let me convince you, not that the harmonic series diverges, because hopefully I already did that. Let me instead show you how simple it is to use the p-series. So the first one we see here, we're given terms. Oops, and I actually see a mistake in here. I'm not sure if anyone else notices the mistake, but there's a pretty healthy mistake here. So, oh, wait, I'll do this. Okay, yeah, it was just a single mistake. This is supposed to be 2 to the 5th. There we go. Okay, so there is my series first. So we're looking at the series. I see 1 plus 1 over 2 to the 5th plus 1 over 3 to the 5th plus 1 over 4 to the 5th. The assumption would be if we went further along, sorry, I should be using my own color here to indicate I'm doing it. If we went further along, it would have general term 1 over n to the 5th, and then of course continue onward to infinity. What is it? Ad infinitum, according to how Mr. Bandy would say it in AP Lang. So from talking here, from looking at this, before we want to start anything, before we want to start doing our analysis, I just want to state what the series itself is that we're looking at. And this is the sum from 1 to infinity of 1 over n to the 5th power. And again, I chose that 5th power based on the fact that 3 of the 4 that I could see have a 5th power. It seems like a fairly safe assumption. So now from there, again, you're going to watch very carefully. This could be tricky. What we're going to do from here is we're going to identify p. No, that looks like lemonade. It's definitely not urine. I can identify p. I thought that was funny, but whatever. Anyway, we identify the p-value. So in this case, p is equal to 5. Now that we've done that, we next compare that to 1. So 5 is greater than 1. Okay, now, how do you finish this off? You say, therefore, the series, sorry, I should write the whole series. The series converges by the p-series test. And typically I don't write by the p-series test, I write converges by p-series. And then I'll often write with p equals 5 greater than 1. But truthfully, we already stated over here that p equals 5 is greater than 1. So as long as you stated it, you really don't even need that thing. And if you want to call it the p-series test, who am I to judge? Call it the p-series test. It's not going to test my patience one bit. We'll press the button. But there it is. That's it. You just have to figure out what p is, compare it to 1, and then state whether it converges or diverges. That's it. It's the whole thing. Of course, you could use the integral test if you wanted to, but why would you want to? Like, I like evaluating improper integrals as much as the next person. Probably a lot more, but this is nice and clean. Having said that, it gets even cleaner if you're given the series at the very beginning. Like, look at this guy. Like, look at this. Does this series converge or diverge? Well, all it requires us to do is, of course, identify p. So our p in this case is 7 over 11. That makes me think of Slurpees. Hopefully we'll be able to go to free Slurpee Day on 7/11. So if p equals 7 over 11, 7 over 11 is less than 1. Sorry, I was using color before. That is less than 1. What that tells me is that our series, 1 over n to the 7 over 11, tells us that series diverges because the p-value is less than 1. So the series diverges by p-series. And we could say test. You know what? I'm just going to stick with it. I'm going to clean all this up. It's not perfect, but it is what it is. So there it is. This series diverges. And again, if you're wondering why I left all this blank space, well, it was to fool you into thinking there's going to be a ton of work. That blank space is for the one person who wants to actually go through and do the integral test every time. I don't want such a thing, so I'm not going to deal with it. So there's p-series. Again, it's pretty consistently straightforward. It's a really clean one to go through, but again, the integral test is at your backing if you choose to use it. Now, having said that, we could ask a little bit more, and I will admit that typically this question is a try it in class, but again, I'm here. This is like the twistiest that you can really get with p-series, so I don't want to just leave you hanging on this one. But basically, we could ask you some complicated questions a little bit, and the try it has kind of a, training wheels version of this question. But basically, looking up here, they give you a p-series, what looks like a p-series, but then they give you a power that's kind of complicated and has some variables in it. And they ask you for what values of m does the series converge. So you want to find what conditions would allow us to guarantee that this was a convergent p-series. So that's what we're looking at in this particular case, is how do we check and guarantee that a particular series is convergent. So having said that, where it begins is by thinking about how p-series work. So notice that this definitely is of the form and the structure that we're looking at for p-series. It fits the form 1 over n to the p. Sorry, that's a terrible p. There we go. So it fits the form. So remember, with p-series, if we want p-series to converge, we want the p-values to be greater than 1. So in this case, it's important to note that in this problem, our p-value is m squared minus 5m minus 5. And according to what we're doing, we want that to be greater than 1. So right there, that sets up our work. This is now the crux of our work. We've transformed it into an algebraic polynomial inequality. So all that's left is we try to solve it. As we go through here and start to work in, though, make sure you don't make the mistake of heading in the wrong direction. To start this off, we want to compare things to 0 so we can focus on signs rather than try to factor things early. So what I'm going to do is I'm going to subtract 1 from both sides here. And that will transform my inequality into m squared minus 5m minus 6, which is greater than 0. Now, from here, this is readily factorable. In fact, I want to say this is m plus 1, m minus 6. So having done that, not only did we make it factorable, whereas the earlier one definitely wasn't factorable, but what we've done is we made it so we can clearly see what's happening here. This is a parabola, and if we ask, when is this parabola greater than 0, what we're really thinking about is a geometric picture. This is the same thing as the parabola, the happy parabola, because of the fact that m is positive. The happy parabola with 0 is negative 1 and 6. So those two things, and we're looking for where this particular thing is positive. Well, that seems pretty clear. It's positive over here, and it's positive over here. Look at that, it's smiling. Like, it's kind of hard to do right now otherwise. So it's positive on those two sides. And since those are -6 and, excuse me, I did it wrong already, -1 and 6, what that tells me is that the intervals for which we are positive, for which we have the p-value greater than 1 then, will be when m is less than -1 or when m is greater than 6. And having said that, that answers our question. The only thing that'd be left is to state it properly and as nicely as we possibly can. We can say that this series, oh, you know what? I've forgotten this whole lesson that I can just copy this series myself. Oh, come on, really? Hold on. I've forgotten that I could just copy this rather than write it over again. I guess that's like fair karma-wise for all the times I did that to you the last few days. So what we've just shown is that that series converges. Converges for m less than -1 or m greater than 6. And again, the way we got there was using p-series, but all that matters is that, of course, we're able to reason it through. And again, it all came back to recognizing that structure of the p-series. If there's one thing that's really important, emphasis on the important part of these p-series, it's recognizing the structure and noticing that, hey, this looks just like a p-series, so it's going to behave like one, and then trying to take advantage of that fact to work through what's there. So having said that, as you'd expect, like to wrap up the p-series portion, I've got a couple questions for you to try it. Like again, just like with the last one question is just simply a recognition and examining, do you recognize like whether this matches the criteria we're talking about of the structure. The other ones ask you to determine whether a series converges or diverges. Unlike the integral test one, this one will move pretty fast, so I'm not too worried about it. But as I said, I did on the last one put in a question, I did put in a question I thought would be a little bit more thought-provoking. Not super difficult, but similar to the last question a little bit. Just to give you a feel for that. And of course the problem sets will do that as well if you're working through and keeping up with those as well. Having said that, obviously, like I hope that you work through the triad here. Hopefully this is a good set of practice problems for the p-series portion so that you can finish this up pretty fast. Hopefully I've moved at a pretty good pace in this one. I'm trying to be as thorough as possible under the circumstances without dwelling too long, and also keeping in mind that of course you can pause and speed me up anytime you want to. I'm not going to be offended. In fact, I can't even tell. So YouTube Studio Beta does not tell me whether or not you sped me up. So do what you need to do. I just want you to learn the material. That's what's important to me. Having said that, let me make sure really fast. Yep, okay. There is nothing else in the lesson. We have hit everything in this topic. So hopefully this has been a good coverage of both the integral test, like how to use it, where it comes from, and like both converge and diverge situations, as well as both the harmonic series and p-series, both really important types of series and simple ones to actually state and decide whether they converge or diverge. So having said all that, thank you again as always for watching, and I will, just like every other day so far this week, look forward to making this lesson tomorrow and pretending that I'm actually delivering it to you in class, pushing that button with other people laughing, not just the electronic button. So thank you again. Stay safe, everybody. Stay well. Let me know if there's anything I can do for you. I miss you, and talk to you soon.